We're going to start with a very famous problem called the Monty Hall problem, named after a game show host. Now the problem goes like this. You have three doors, door number 1, door number 2, let's call them door number 3, and behind one of these doors lies a brand new car, whereas behind the other two doors lies a goat. And you are a contestant in this game show and you need to pick one of these doors. If you pick the door with the brand new car, you get to take the car home. If you pick the door with the goat, you get to take the goat home. So let's say you pick door number 1. Now what Monty, the game show host, does is he opens one of the other two doors, door number 2 or door number 3, which has a goat in them. Let's say he opens door number 3 and shows to you that there's a goat in door number 3. Now you as a contestant are given a choice. You can now change your door number 2, or you can keep the same door, which is door number 1. What do you think you should do? Intuitively it makes sense that both these doors have an equal chance of probability of having a car, because there's one goat and one car and there are two doors and there's an equal chance of them being in each of the doors. However, the math says something completely different. The math says that it's always better to switch and gives a 2/3 chance of winning if you change the door. And the answer to that lies in something called conditional probability. In this lesson we're going to try to understand what conditional probability is and also try to visualize conditional probability using one or two techniques. So let's start out with a problem. Let's say we have two boxes and let's call these box number A and box B. Let's say box A contains 5 red balls and 4 green balls, and box B contains 2 green balls and 3 red balls. So the question is, if I were to pick a ball at random from any of these boxes, what would be the probability that it would be a red ball? Now we know that probability of any event happening, if the events are all equally likely and the events are finite, is the number of favorable outcomes by the total outcome. So n of favorable outcomes divided by n total, which is the total number of outcomes. And here you know that if you look at all the number of balls, the total number of outcomes will be the total number of balls, which is 5 plus 4 9 plus 3 12 plus 2 14, and the favorable outcomes here is of course the probability that the ball is red, the event where the ball you pick is red. So the total number of balls that are red is 5 plus 3, which is 8, and you have the probability of 8 by 14. Similarly, the probability of a green ball is going to be favorable outcomes 4 plus 2 6 divided by total, which remains 14. Now what if I were to tell you that you have to draw only from box B, and I were to ask you the probability of the ball being red given that you've drawn from box B? Notice that I've introduced some conventions here. The upward slash indicates given. The quantity to the right of the upward slash indicates the condition. In this case, the condition here is that the ball is being drawn from box B, and the quantity to the left of the upward slash indicates the event that I'm interested in this case the ball being red. Now we know that the sample space has changed right now. Initially we were looking at 5 plus 9 plus 3 plus 2, all the balls in A and B. Now we're just looking at the balls inside box B because that's the condition given, and hence the total number of outcomes becomes 3 plus 2 5, and the number of favorable outcomes, which is 3 red balls in box B, so the probability becomes 3 by 5. Notice that P of red given B is different from P of red probability the ball is red, because you've changed in a sense the sample space. Now what if I were to ask you, what is the probability that the ball is taken from B given that the ball is red? What if I were to take a red ball and I were to ask you, what is the probability that the ball was taken from box B? This again would be the total number of outcomes now would be the total number of red balls, which is 5 plus 3, which is 8, and the number of favorable outcomes would be 3, which is the number of red balls in box B, and the probability here would become 3 by 8. Notice again that probability of B given red and probability of red given B are two completely different quantities, and this is of course because the sample space in both of these are different. Now another way to visualize conditional probability is using Venn diagrams. Let's say there are 100 people, and out of these 100 people, 40 of them like only apples. So 40 of them like only apples, 30 of them like only oranges, and let's say 20 of them like both oranges and apples. So what is the probability that someone who likes an apple also likes an orange? In a sense, what I'm asking is, what is the probability that given someone likes an apple also likes an orange? And visualizing this data set straight away is a little bit tricky, and what can really make this easier is by drawing something called a Venn diagram. So I'm going to draw a box that basically represents the entire data set, which is 100 people. The first circle is going to represent the number of people who like apples, and the second data set is going to represent the number of people who like oranges. And the middle portion here is going to represent the number of people who like both apples and oranges, and hence that portion is going to contain 20 people, while the number of people who like apples only, this section, will contain 40, and this is going to be 30. The remaining 10 people we don't have any data about, so I'm just going to keep them here in the universe. Now this makes it a lot easier to visualize. So we know that probability, again, number of favorable outcomes divided by the total number of outcomes. And here the data set, given that the people like apples, so that's going to be the total number of data points that we're going to look at the 60 people inside here. So the total outcomes become 60. The number of favorable outcomes, which is probability of people who like oranges inside this 60, is going to be just this 20 over here, because these are the only 20 people who like oranges and apples, and this is going to be our final probability. Now what in essence we've really done here is we've started out with the number of observations in apples intersection oranges, number of people who like apple and oranges, which is the intersection over here, divided by the number of people who like apples, the total number of people who like apples, which is 40 plus 20, which is 60. Now dividing these both by A intersection O divided by just the total number of people, dividing the numerator and denominator by total number of people. So this essentially becomes P of probability of the A intersection O, apples and oranges occurring, divided by the probability of only apples occurring. And this essentially is the formula for conditional probability, which says P of any event occurring given B has occurred is P of A intersection B divided by P of B. So just summarizing what we've done in the lesson so far, we saw that the notations where this is indicated by what is given, you have the condition here, and you also have the event that you're interested in. And when you put a condition, essentially the probability changes since your sample space changes, and is essentially different from P of A. We also saw that Venn diagrams are a great way of visualizing conditional probability, and we also saw how the formula of P of A given B is equal to P of probability of A intersection B divided by probability of B really made sense using Venn diagrams.